And that's trying to build a self-driving database management system and the fact that my wife is pregnant. And so I realize that sometimes I say crazy things in talks and people are not sure whether I'm serious or not. So this is real. This is a picture of my wife. That's obviously not my child, but like she's pregnant. This is real, this is happening, right? And so the reason why I'm freaking out and so stressed is that I have to confess that I'm completely unqualified for both these things. Trying to build a self-driving database system and trying to help my pregnant wife. And the reason is because I've actually never taken a machine learning course, and I know nothing about pregnant women because I never took sex ed. So when I was in grad school as an undergrad, it was before sort of machine learning took off. I've taken optimization courses, I've taken linear algebra, but what we would call today a traditional machine learning course, I haven't taken that at all. So everything I know that I'm going to talk about here today are things I picked up off the street, working with other researchers in the machine learning department at CMU, and just reading papers and other blogs. The other thing I think also admit is that I never took sex ed. So this is not like because my family was religious or anything like that. It was just because when I was in middle school, when they separated the boys and the girls, they put me in another room because I was deemed too emotionally immature to take sex ed. And they maybe thought I'd never meet a girl or something like that. So I know nothing, okay? So the only thing I know about pregnant women actually comes from this 1993 episode of Perfect Strangers that I watched when I was 12 years old. If you've never heard of Perfect Strangers, that's okay, it was a crappy show. But in this particular episode, the one guy who's living in the house, his wife's pregnant, and then his buddy, his wife's pregnant. And so the only thing I learned from this, and I sincerely remember this when I was young, is that pregnant women get tired a lot and they eat a lot of pizza. That's the only thing I know about pregnant women, right? So this is problematic because I want to help my wife get through this, and I don't know how. So what's something I do know about? Well, I do know something about databases, so let's talk about that. So the goal of a self-driving database at a high level is that we want it to be entirely autonomous. And so my definition of an autonomous database system was one that can remove the burden of having humans to basically babysit and maintain the software. Humans are very expensive, database systems are very complex pieces of software, and so you have to have, ideally we don't want to have the human make all those decisions. So the kind of things we want to target in an autonomous database system, again, are the classic things that DBAs do today. Physical database design, things like picking indexes, sharding keys, data layout, knob configuration tuning. So a knob would be the parameters that can control the runtime behavior of the database system, buffer pool size, and things like that. And they also can do query plan tuning, like picking join order, picking indexes for expensive queries. And then what's more common now today in more elastic or cloud environments is doing capacity planning or hardware provisioning. So when you talk to DBAs, when you look at the surveys, these are the things that they're spending a large percentage of their time doing. And these are the kind of things we want to automate. So this idea of autonomous database system is not new. It actually goes back to the 1970s after Ted Codd published the seminal paper on the relational data model. People soon realized that since we're hiding away the underlying storage and execution strategies of the database system through a declarative language like SQL, somebody needs to figure out how to actually tune the internals for each application and each workload. So at a high level, what I'll say is that in the modern era, the methods that we're going to use look very similar to what people did back in the 1970s. Right? The algorithms are different, we're doing machine learning stuff, whereas back then it was more heuristic based, but at a high level it's still the same thing. You look at the workload, you look at the database, try to extract some meaningful signal, and then you try to tune for the given application. So the other difference too is also, they weren't calling them self-driving databases. Back then they were called self-adaptive databases. So there's this great paper from 1976 written by Michael Hammer on doing a self-adaptive database system that can pick its own indexes, right? So again, this paper was written by my advisor's advisor, who's dead, right? So people have been thinking about this for a long time. In the 1990s, again, the label changed. These became self-tuning systems. It's my opinion that I feel like Microsoft was at the forefront of this movement with Surgeon Chaudhry and the Auto Admin Project. And there's this great paper in DODB 2007. It's a 10-year retrospective of all the various things that they tried to solve, and challenges they faced at Microsoft. So now in the 2010s, we're entering the era of what people are labeling as learned components. So if you read Hacker News, if you're on Twitter, these are the kind of things that you've probably been seeing about and people have been talking about, how to make database systems work in a modern era. So I want to talk a little bit about these learned components, and you'll see why these are, what, in my opinion, evolutionary rather than revolutionary, meaning they don't solve the problem of having to have humans maintain the software. These are just making these systems work better than they already do. So the paper you're probably most familiar with is on the learned indexes. So at a high level, it's pretty straightforward. You have a B+ tree in your database system, keys go in, location comes out. So just replace this data structure with a trained neural network that approximates the same thing as a function. Given key, what's the location of the database on disk, right? So again, this doesn't say anything about what indexes you actually need. This is just a potentially better data structure than a B+ tree. You still have to have a human or some other higher level planning component decide, oh, for these keys, I want this index. And then whether I want to use a B+ tree or a learned index, right, it can make that decision as well. People have also looked at using machine learning for scheduling and sharding. So in a database system right now, you have this partitioning scheme that's usually handpicked by a human or a simplistic tool. So for a given transaction, I want to decide what queue to put it in, right? And then, depending on my objective function, I can try to say I want to minimize latency or spread the data out as much as possible. Right? You can do different things for these. So what people have done is they've trained unsupervised clustering algorithms to be able to extract some meaningful information about these transactions and then use that to make the decision of where to queue these things up, right? And so, again, whatever your objective function is, these algorithms can still just work. You don't have to change any of the underlying search process. The one area that I'm probably the most bullish on, although this is not my own research, is doing learned planning. So this is using machine learning to augment or enhance the decisions that a query optimizer actually makes. So basically what happens is SQL query shows up, we turn this into a logical plan, right? And now the query optimizer has to figure out for these different operators, what's the cardinality? How many tuples are these things going to emit? And so traditionally a database system would use histograms and sketches or other approximations of the contents of the database to make these decisions. And so instead of using histograms, you can train a neural network to try to approximate this. So again, this is the one I'm the most excited about. I think this is the one of all of these different domains. It's probably going to be something that can end up in production within the next 10 years. If you're interested in this kind of stuff, there's a PhD student out of Brandeis, Ryan Marcus, who's now a postdoc at MIT. He has a lot of papers in the archives in this area. That's pretty exciting. And so again, but this is also not a new problem, right? IBM had the Leo, the learning optimizer, published in 2001 that wasn't using machine learning, but the basic idea was the same, that you imply information you get when you execute the query, and you improve the approximations you're making in your query optimizer. So again, all of these are very exciting, all of this is good work, but this is not replacing the human in the loop. So that's what a self-driving database attempts to solve. So a self-driving database system is one that's able to configure, manage, and tune and optimize itself automatically without any human intervention or input during the lifetime of the system. No matter how the workload changes, no matter how the database changes or how the hardware changes. So the only thing the human has to tell us is when we turn the system on, what is our objective function and constraints. So the human has to tell the system, oh, I want to minimize latency, maximize throughput, minimize hardware costs. And then here's some SLOs that I have to meet for my transactions or queries. Or here's your budget for how much you can spend on hardware. But beyond that information, we should never have to go back to the human and keep asking for more input, more guidance. So the self-regulated data system will be able to handle all the things I talked about at the beginning that human DBAs are doing today, with a small exception. And that is the system is not going to be allowed to tune anything that requires a human to make a value judgment about the correctness of a decision. So the example I always like to give is, say there's a knob in your system to turn off fsync, all right, turn off writing data to disk. And if your objective function is to run as fast as possible, the machine learning algorithms will learn pretty quickly, if I turn off writing data to disk, I'm going to run faster. But of course now, if my system crashes and I lose all my data, my company or organization or whatever is dead because I lost everything. But that's an external cost that the machine learning algorithms can't take into consideration. Right? Other things would be what isolation level to run transactions in, right? Because that depends on how many anomalies you want to have. All of these are things we can't reason about. These are humans have to tell us this. And so the machine learning algorithms will be explicitly denied or blocked from modifying this thing. So at a high level, it's going to look like this. So I'm showing this drawn in two separate components, right? But this could be running in the same database instance, or these could be running as a separate machine as services. It doesn't matter for our purposes here. So again, the human tells the agent, this is my objective function, these are my constraints, provides that as input to the agent, who's then going to now select an action to apply to the database system to make a change that it thinks is going to get the best benefit out of. So these actions are inherent or built inside the system. These aren't something the human has to tell us. Right? These are like all the knobs I can tune. Here's the callback function to make the change. Here's all the table indexes I could deploy. Here's the hardware choices I could have if I want to scale up or scale down. Right? These are things that we have to be built inside the system. So we apply the action, and then we're going to get feedback of the new state of the system and the reward that we got. So the overarching goal of what we're trying to do here is that we want to train a policy that allows us to make a decision for what action to apply under different scenarios, for our current state. Right? That's the overarching goal for a self-driving database system, at least for my own research. And I'll say that I haven't said anything of what machine learning technique we're using here. So I'm not going to talk about reinforcement learning. I'm not going to talk about Monte Carlo tree search. All of that doesn't matter. We're just trying to understand how we can actually achieve this kind of infrastructure. So what are the tenets we want in our self-driving database system? What do we actually want it to have, or be able to support? So the first is that we need to support unknown configurations. So what I mean by that is that there are certain actions we can apply that we don't know anything about. And we have to allow the system to be able to deploy them, observe whether it was a good thing or not, and then potentially roll back if necessary, or revert them. So that means none of our actions are destructive. Right? They're always reversible. So we're never going to throw data away, drop a table. We're always able to apply a change, and if it turns out to be a bad idea, we can go back. The next thing we need to be able to do is to generalize about different environments, different workloads, different applications, different types of hardware. Right? And so no matter what system we get deployed on, that we can learn something from that and extrapolate information that we can then reuse for other deployments. Right? So think about this. Every single time I deploy the system on a new application, I don't want it to learn from scratch all over again, because that's going to take a long time. I want to take all the information I've gained from previous deployments and apply them to the new scenario. It may not be perfect, but at least it'll bootstrap me towards the right direction where I need to go. The last one's the most trickiest one, is that we need to be able to reason about delayed consequences. So people do this now in database systems. Black Friday or Cyber Monday, it's a big spike in traffic if you're an online retailer. So a month before, they are preparing their databases by moving data off, scaling up, tuning the knobs, in preparation for that big spike. So the changes they're making 1 month before, they're not seeing an immediate benefit, right? Because the spike of traffic hasn't came yet. So we need to be able to make these kind of changes in anticipation of something that's coming up in the future. So again, I would say these three tenets are not specific to database systems, but they are harder in our context. So if you're using machine learning for other aspects or other domains, all of these problems are still applicable, but in our world it's much harder. Right? If you think about this, like the DeepMind, when they're playing Atari games, like moving the little character left and right, that's cheap for them. Right? That's their action space. In our world, for to build an index, it might take 6 hours. That's expensive. So we need to be more careful about how we do these things. All right, so for this talk, I want to talk about the hard parts. So this is a depressing talk, or pessimistic talk, meaning I don't have answers for you. These are sort of the challenges that we're working on at Carnegie Mellon, and these are the challenges that other people should be looking at as well. So there's no graph at the end of the slide where like everything's going up a quarter and everyone's happy and we change the world for the better. I don't have answers for most of these things. So first we'll talk about how to do state modeling, how to collect the training data we need to then feed these models, and then we'll finish up talking about how we want to observe the rewards we get from actions. Now as we go along, I will show this icon here of the sonogram of my wife with the label hard, just to make it clear that these are the hard parts that I'm talking about as we go along. Okay? All right, so the first thing we have to do is model the state of our database system, like essentially modeling the environment. And to go back to my pregnant wife, the way I'm going to try to tune my database system is actually very close to how I actually want to help my wife, right? And so before you get weirded out thinking I'm treating my wife as a machine learning problem or like a robot or things like that, you have to understand that I only care about two things in my life, right? The first thing is my wife, the second thing is databases. I don't care about anything else. I don't talk to my family. They support Donald Trump, so like I haven't seen them in months, right? I don't talk to them. And so this is actually a screenshot of one of my lectures in my class back at Carnegie Mellon. So every single semester on the first day, I show the students this slide, just to get an idea of like how serious I'm about, like hardcore about databases. She's number one, databases number two, right? So let's try to help number one first. So in order for me to help my wife, I need to understand what's going on. And again, I know nothing about pregnant women because I never took sex ed, so I have to try to figure out how to model her state to then figure out what actions apply to make her feel better. So this is kind of hard, right? So the first issue is that my wife is stochastic. So what I mean by that is I can't actually see what's going on inside of her at any given time, right? Meaning like, because you can't do surgery, you can do a sonogram, but that's an approximation. So it's really hard for me to figure out, what's her current state right now. I sort of have to take a best guess. The next issue is that she's non-stationary. So it doesn't mean she's not walking. It just means that from day to day or hour to hour, any action that I have to make her feel better, or try to make her get through the pregnancy, I might not get the same reward the next time I try to apply it. So she tells me she's hot right now, so I turn the AC on, and then she tells me she's hot again, and turn the AC on, the same thing. She's like, no, don't do that, that was a bad thing. I feel worse. Right? So it's very hard to kind of sort of converge on your model to figure out how to make my wife feel better. And the last thing, which is a good thing, is that her pregnancy is episodic. So this thing will be over in 9 months. It's less than that because it's coming up soon. And so that, from a modeling standpoint, there's in machine learning, because we know we have an end state, there's different ways to simulate trajectories and things like that about the behavior of the system. And so in my wife's case, a little bit easier because I know there's an endpoint here. All right, so let's go back to databases and see how this all fits together. So a database system is going to be the first two, but not the last one. So the database system was going to be stochastic, meaning we can never know exactly what's going on inside of it at any given time. We can never look at exactly, here's all the contents of my data. We can't look at every single instruction the CPU is executing, so we're going to have to approximate it. And again, this will have some problems because we'll end up with our estimations of what the state is will be wrong. The next issue is that it's non-stationary. Again, that means that if I apply an action today and I get one reward, I apply another action and the same action at another time, I could get a different reward. What was a good index this week is a bad index next week because my workload has changed, my database contents have changed, right? It's hard to be able to reason about that. And the last one is that the database system is non-episodic. So if you're a database vendor, as long as the customer's credit card keeps clearing every month, this thing has to run forever. So that makes it a bit trickier about how we have to predict what a horizon is or how long we want to look in the future and prepare for changes. And we can't assume that we're always going to get to some terminating state. So that limits some of the machine learning methods we could possibly use. All right, so to model our database system, we're going to use an MPP, or Markov Precision Process Model. So the only thing you need to know about is the word Markov here. And that just means that how we encode the state of the database needs to encompass the entire history of that database system, or database deployment. Right? So like for every single action, like if I'm building an index, I want to encode every single index that I have and not have some sort of separate side thing that says, here's the actions I applied. Right? And so what we're going to code in our state vector for our database system is the current contents, right? What the values of the columns are, the physical design, indexes, sharding keys, and so forth. What the workload looks like now and in the future, like what queries I think I'm going to execute, at what interval, at what arrival rate, the current knob configuration, and then what our hardware resources look like. So all of these are going to have a bunch of problems that are going to make this machine learning side of things very difficult. And so I want to focus on database contents first, because then this will make it clear, how these problems apply to other things. So let's say we have a really simple table here. We have 4 columns, right? It has 2 ints and long and a bar chart. And let's say now I invoke an insert query that's going to sort 1,000 tuples with some random data. So this is Postgres syntax. I don't know if you guys can see it in the back, but basically I'm inserting 1,000 tuples that have the increasing key value is the first one, the repeated value for 99 over and over again, and then a random integer and random string. So now, I want to build a state vector that represents the contents of this table, right? And then I'm sort of take a snapshot periodically and produce this state, because then I can use that to figure out what action I want to apply. So a really simple thing to do, which is to say I have 1,000 tuples and I have 4 columns, right? That's pretty straightforward. And then for the first column, I would encode some basic information like what the type is, what the min value, the max value, the cardinality, right? And I'm going to do this for every single column that I have. So again, what we're trying to do in a self-driving database system is learn a policy that can pick an action for a given table state, right? We would repeat this for every single table we have to say, what benefit I would get for a particular action. So a really simple thing here is, again, if I want to add an index, I would know for the first column, I only have one unique value, right? It's 99 repeated over again. So that means building an index was a bad idea because I'm not going to get any benefit from it. But the first column has a cardinality of 1,000. So again, I can learn a policy that says that this is a good idea, I should have an index for this. Right? At a high level, that's essentially what we're trying to do. So these vectors for every single table always have to be the same size, right? Because it's all our history of the training data that we've collected for every single time we take a snapshot of the state of the database. So what's the problem with this particular state vector? What's the one DDL command I can do that would cause this to get invalidated? What's that? I heard it. You can say it, you already know.
Well, the space can change. Well, the number of states can change. The number of parameters can change.
He said the number of parameters can change. Correct. So if I add a column, I add a 5th column, now I need to have an entry in my state vector for all the contents of that 5th column. But I don't have that for all my previous training data. So I have to throw it all away and start collecting new training data. So then you can say, all right, well, maybe you need to go back and just fill in a bunch of zeros for the 5th column you didn't have before in all your old training data. Well, that wouldn't work either because that's not correct either, because that column you could have had some real data, but you said it's zeros, and therefore you'd be learning a policy that is incorrect. Right? So this is hard. We don't know how to handle this. All right. The next issue is that we're taking a gross approximation of the contents of the table, and this is going to cause some problems when we actually start making selections of the actions. Right? So let's say I have a simple query like this. It's doing a self-join, and my database system or my agent wants to say, I want to go to index to speed this query up. So I have my state vector, that's again a snapshot that I showed in the last slide of what I think the state of the database is, the state of this table. And through some other calculation, I can say, here's the benefit I think I'm going to get. So the reward for adding this index would be 100. It's a synthetic number, it doesn't mean anything. It means good, right? The problem is, again, this is an approximation of what we think the database looks like. And in actuality, this estimated state could map to multiple real states. Right? This is called aliasing. This is where I think the world is a certain way, right, at a lower resolution, but when I look at the full picture, I can see that my low-res image can map to multiple states. So if my estimated state maps to the one at the top, then yeah, I get that reward of 100. But if I map to this one at the bottom, then now I get a negative reward, right, for adding that index. So I try it, and then it turned out to be a bad idea. So now I'm getting feedback from my agent that said, hey, you added this index, but that was a bad idea, don't do that. But this is problematic too, because we actually don't know what the real state is, right? We only know what our estimated state is. So the feedback we're getting is, for this estimated state, when I deploy my index, I got back a negative reward, right? So again, that's problematic because we might have been mapped to the state at the top, and therefore it would have been a good idea, but we got to the one at the bottom, because that's what the real database looked like, and we got back a negative reward. So we end up learning that picking indexes for that particular estimated state is a bad idea. So then you say, all right, well, how can I get the real state? Right? Well, I can run analyze. This is what the optimizer does, the database systems do now. You basically do sequential scans of an entire table, and you extract out the information to get the real content. So the query optimizer does this all the time. So the problem is, if I get my actual state, say that it took me 3 hours to run analyze, but then it also took me 3 hours to build the index. So my actual state is now 6 hours in the future from what I was when I did my estimation. So now I got to figure out how to go back in time and derive that that real state, where I was at the time I deployed that action. So you could try to replay the log, you could try to take a snapshot and things like that, but that's not free, right? Those things are expensive to do. So how to actually handle this and get the correct feedback we need to say, my state looks like this, here's the word you're actually really going to get, is hard. We don't have an answer to that. All right, so let's look at knob configuration, right? Because you can see similar issues. So again, the database knob configuration state is just, here's my current parameter settings. And I can take this every single time I take a snapshot from my database state vector. So I can record some simple things like, here's the number of threads I want to use to execute queries, here's how much memory I want to use to allocate for different components of the system, like the buffer pool size or query cache. And so I can collect a bunch of data here on a machine that had 32 gigs of RAM. Right? And so in this case here, these memory configuration parameters, these knobs, are perfect for a machine that has 32 gigs of RAM. But then now I come along with a machine that has 128 gigs of RAM, and all of these absolute values now in my state vector are invalid for me because this is assuming I had 32 gigs of RAM before. So how to be able to extrapolate this data that we have collected on smaller machines and apply them to other machines that have more capacity or better hardware is a hard problem that we don't exactly know the answer to yet. We have a way we think we can do this, and I'll talk about the next slide, but we haven't vetted this yet. All right, so now the next issue is very similar to the add drop column example I showed 2 slides ago. So in some systems, you can actually create components on the fly. They each have their own configuration knobs. So I'm using DB2 as an example here because it's pretty straightforward, but we've done a survey on a bunch of different database systems. They all have similar issues. So in DB2, you can create buffer pools on the fly. And for each buffer pool, they have their own knob configurations, like the page size and the block size. So now I need to have an entry in my knob configuration state for those separate parameters. But the DBA or somebody can keep doing this over and over again, creating new buffer pools, and now I got to add new entries. So the same problem we saw when we did add drop column, now the dimension of my feature vector is going to change, and I have to throw away all my training data. So actually how to handle this, again, is hard. We don't have an answer to this yet. All right, so I have some potential solutions for these things. So something might be to just reduce the dimensionality of our feature vector. If you talk to any machine learning person, right, this is the first thing they'll say you should do. The problem with this is that when you reduce dimensionality, you're essentially destroying data. So PCA or autoencoders or hashing kernels, they basically take a high dimensional feature vector and condense it down to be a fixed size. Then I can use all the training data that I've had before. They're always that same size. And so this works great for things like ImageNet, all those deep learning models that can identify dogs in pictures. Essentially what they're doing is they're taking a high dimensional image that's an arbitrary of dimensions and reducing it down to a 128 by 128 image. Because all the models are trained on that. So we can't do that in database systems because we need that fine-grained or precise information to know what action to apply. I need to know that column only has one column, that column only has one unique value to know that building an index on it is a bad idea. And so if I use something like a hashing kernel, all of that gets destroyed and I may never converge to find a good solution. To handle the problem I showed in the last slide about the hardware knobs being absolute values, we think we could store them as percentages and just record the hardware information as a separate features. And that way, if I know 90% of memory on this machine for this workload is a good idea, 90% memory for the buffer pool on this other machine would also be a good idea. But like I said, we have not tested that yet. And the last piece where we think we're going to handle the issue of changes in the environment or changes in the system that cause us to have to invalidate previous training data, we think we can model a system in a hierarchy and have separate models for different components of the system so that if one piece changes, maybe you only blow away data for just that one part. It's isolated from the entire system. But again, we haven't vetted that yet. All right, so next we need to talk about is how we're actually collect training data to feed these models. Again, we're going to use this to be able to bootstrap what the system is actually doing so that we don't have to learn from scratch all over again every single time. So again, going back to my wife, I want to make her happy. I want to try to figure out how I can do different actions to help her feel better. The problem is that I don't know any pregnant women. This is not legal in the state of Pennsylvania, but I tell all my students, don't get pregnant, don't get anybody else pregnant while you're in grad school. So I hang around a bunch of 22-year-old kids that aren't pregnant, right? And so it's very hard for me to get training data. My wife, I don't know why she married me, but I'm clearly trying her patience when every single day I'm saying, try this, try that, because I'm trying A/B experiments on her to see whether I can make her feel better. And after like 2 of them, she's like, go away, I'm gonna kill you. So I don't know how to get training data. This is very expensive for me to do. So again, I don't know any pregnant women, so I did the next best thing. I went to Craigslist, and I said that I was seeking to gain experience with pregnant women. It wasn't like a weird fetish thing. It was just like, hey, look, I don't know pregnant women. Let me come over to your house, watch you be pregnant, and I'll take notes, and I'll go home and try to apply the same thing to my wife. Craigslist took it down in 2 days. They were not happy about this. But I could see how it could be misconstrued as something weirder than it actually was. All right, so I can't get training data for my wife, but we can get training data for databases. So there's 2 types of training data process we're going to have. For training data collection. The first of that, we do offline acquisition, where we're going to run targeted workloads in the background at night in spare machines to do parameter sweeps across the entire configuration of the system. The second one is online acquisition, where while the system is actually running in production, we'll observe the behavior of that system, we'll apply changes, and we'll target or refine our models for the particular application that the system is running on. So I'll go through both of these. So for offline training, there's 2 ways to do this. So the first of that, you can do these end-to-end benchmarks. We're going to prop up the full system and run your favorite sample workload or TPCC benchmark, and then use that to understand how the system behaves. Right? So most database systems are broken up into layers like this: planning, execution, storage, and logging. Right? We have these APIs between them. So the agent can come along, pick your favorite benchmark, prop it up, and start issuing SQL queries to the full system. It tickles the entire stack, and we get out the metrics we want to train our models. So the other type of offline training we can do are these sort of targeted component trainers or mini trainers. So the idea here is that we're writing micro benchmarks that target one specific component of the system, and therefore we can do a more complete, comprehensive sweep across all its different configurations and collect way more training data more quickly than we can do with the end-to-end benchmark. So the agent says, all right, here's my micro benchmark. I only want to touch the storage layer, so I'll invoke the underlying API of the internal API of the storage layer. Again, do whatever it is that it's designed to do, and then collect training data that way. And the benefit of this approach is that if I end up going and replacing the storage layer with a new component, I have to throw away all my training data that I've already collected because now the system's behavior has changed, but I only need to run maybe my targeted micro benchmarks. So you want both because these different layers are not independent of each other, but the mini trainers allow you to converge more quickly. At Carnegie Mellon, as we build our own database system, we're treating this idea of modeling and data collection as a first-class engineering principle. So anytime a student writes a new feature, writes a new component in the system, they have to write the documentation for it, write the testing code for it, and then they also have to write the mini trainer for it. And then we have infrastructure set up to allow us to deploy this and collect all this training data that we need. So real quickly, just to show you the difference with these two as they collect data. So this is running in our own system at CMU, where we're testing out the logging component of the system and trying to model its behavior. How fast can it write log records out to disk? So the main takeaway here is that if you run the end-to-end benchmark with YCSB, it takes 40,000 observations for it to get an accurate model of what the system actually, how the system behaves. But in the case of the micro benchmark, we can do this in 1,000 observations, right? Again, you need both because there are interactions between different layers that you can see the noise on the end-to-end benchmark above the main curve, right? We want to capture that information, but to get a complete span of the solution space or the different parameters, we can do that more quickly with the micro benchmark. All right, so we run the offline training data. This allows us to bootstrap our models so that we're not starting from ground zero for every single deployment. But then as the system is running, again, we would collect the same data, and then we can refine these models to improve the accuracy of our decision making for the real system running in production. So because we're running in production, we need to be more conservative, more careful with what we're doing, because we don't want any observable effects to be exposed as we apply actions and collect training data to the end user or the application. right? So at no point should they see missing data, should they get their connection severed, right? And performance dropping down. Performance can go up, but it can never go down. So how are we going to do this? Well, we could just prop up a new machine, clone the database, clone the workload. Like all the major database vendors have tools to do this very easily, but that's expensive. And so instead, what we think we can do is actually piggyback off of the high availability mechanisms that every single database system has, use that as our method to train and collect training data. So let's say we have a real simple setup. We have a single master and 2 replicas, right? The agents trying out different actions in the background on the replicas, right? Whereas the master always has whatever the best configuration we've ever seen before, right? The best indexes, the best knob configuration of all time. So now if the replica identifies, hey, here's an action, here's a configuration that I get a better reward than what's on the master right now, that can end up getting promoted and applied to the master. So again, we can do all these changes in the background on the replicas, and the end user doesn't see these things. But the downside of this is that, in this case here, the actions made us go faster, but what if the action actually makes us go slower? And so now we need to be concerned about the failover time, because if our system falls behind from the front end, and at any given time the master could crash, and now the replica becomes the new master, but it takes us 20 minutes to catch up on the log because we're in a bad configuration state. So how to actually handle this is tricky. One simple way to do this is maybe declare one machine is the slower one machine is the faster one. So you're more aggressive on the slower machine, trying out actions you don't know anything about, and then you're more conservative on the faster machine. Right? So that way the likelihood that both the master and the faster machine go down within the same time window is minimized. So how do you actually handle this and keep track of the failover time while you're doing training is hard, and we don't have an answer for this yet. All right, so now, again, the application server is sending reads and writes to the master, and the master sends the writes to the replicas. They replay them, and that's how they stay consistent, right? But what do database systems do now, right? What do these writes actually look like? Well, they're usually the op log, or write-ahead log, right? The low-line physical changes to the database itself. The problem with this is that if you're only applying the op logs, then you're only really touching like the log manager and maybe the storage manager. So the upper levels of the system, like the execution engine, the optimizer, you aren't going through those layers. So you're not going to collect any training data for them because you're only touching the lower parts of the system. So then you say, all right, maybe I'll send the SQL queries, and that way I can just re-execute the entire query, and it'll mimic the behavior on the master. Well, the problem with this is that the SQL queries can be more expensive to execute because, again, you're going through the full stack and you're in a bad configuration state. So how to actually handle this is hard. We don't have an answer to that yet. All right, so now you say, well, I'm only seeing the writes as well, so I could come up with configurations to make the writes go faster, but I want to maybe send the reads to the replicas. But the problem with this one is the application server could be sending any possible read, and you don't know whether that's representative of what the master is actually seeing. So we think there needs to be some metadata passed along from the master to the replicas to say, hey, here's what the real workload actually looks like. So this is actually called, in machine learning, this is called active learning. Because we essentially want to learn how to learn. We want to be able to learn what do we not know about in our replicas and our models, and have the master propagate just the minimum information that we need. Like, here's all the read queries that touch this index and you don't know anything about. We send those to our replicas so that they're not, they're not trying to execute the full workload, which may be difficult to do if you're running slower. So actually handle that is super hard. We don't have an answer to this yet. All right, in the sake of time, I'm going to skip this very quickly, but basically, the hardware, you can't assume the hardware is the same, and you need to account for that in your models. And that's hard. All right, so the last thing I want to talk about is how to observe the rewards. So again, we want to be able to say, if we deploy an action in our system, how can we keep track of whether that was a good thing or not? So again, going back to my beloved wife, there's basically 2 types of rewards I can observe. There's the short term and the long term. So the short term would be like, hey, I don't feel good, and I give her a glass of water, and then she says, oh, now I feel better. Like, I hear back right away, that was a good thing, right? Or like, I don't keep her near open flames, I make sure she's not drinking, like Drano or poisonous things. I know right away that those would be bad, and I avoid those things. It's the long-term rewards that are more tricky. How do I know whether we're doing things now that's going to help my child in the future? So again, I need more training data to try to figure out what's the right thing to do. But again, I don't know any small children. My brother had a kid, and he's on the Trump train. I haven't seen the kid, right? So like, I don't know any small children. So I figured now I gotta do some experiments and bring some small children to me at CMU. Well, the problem with this is that the state of Pennsylvania passed a law in 2014 called Act 153 that states that if you're an educator or a professor and you're gonna be around small children that are under the age of 18, you have to get certified by the FBI that you're not a pedophile, you're not a sex offender. So I'm very proud to announce here at the LDB in 2019 that I passed Act 153 and I'm actually cleared. So I'm actually allowed to be around small children. So I figured, again, let's go back to Craigslist, right? Let's put an ad out saying I'm looking to hang around small children. And I said clearly that I'm Act 153 certified. So I figured it'd be no big deal. So after long conversations with my lawyers, things have been cleared up. And I'm happy to say I'm able to travel and be here. But let's just say I wasn't able to get any small children to hang around. So I have no training data for my life on this part. Okay, so for databases, short-term rewards are obvious. We know whether we're running out of memory, right? It's the long-term rewards that are more tricky to do because we don't know whether the changes we're making are because the environment has changed or because that was a good action. And this is tricky for two reasons. So the first is that the hardware you can't assume the hardware is going to be perfect forever, right? It never is perfect. So we could apply an action, we get a negative reward, and that could be because the hardware, the SSD started shitting the bed. And so we need a reason about that when we observe these effects. So a really simple thing to do is just maybe run micro benchmarks every so often to see whether the hardware matches what now what we saw in the past, and then we observe that it doesn't match, then we can maybe discount the data we've collected so far. There has been some work on trying to train classifiers to identify when hardware is going bad. So there was a Kaggle contest a few years ago where they looked at a bunch of SSD information from Blackberries, and they tried to identify when our SSD was going to go bad. The results were inconclusive. One of my PhD students worked at 7 years at Western Digital, and he said all the smart stuff that the firmware gives you is all crap anyway. So we don't think that's the right way to do this. The running the micro benchmarks is the way to go. But how to actually make this work in your models is difficult. We don't have an answer to this. All right, so I'm going to skip this for the sake of time. I want to finish up talking about what we're doing. So at this point, you may be thinking, well, Andy, I follow you on Twitter or whatever. Weren't you building a self-driving database system at CMU? Right? Why aren't you here talking about that? And so yes, we were building a database system at CMU. It's called Peloton. So the internal details of it don't matter, right? Again, but we were pitching this as a self-driving database management system. So Peloton was a great name for a database 3 years ago when we started, right? And then these assholes with the bike came out and have a lot of money and they have a lot of stores everywhere. So these are photos that my friends sent me saying like, oh, haha, the company stole your name, right? And then I took this photo this morning. This is in the gym on the 3rd floor. They have a bunch of Peloton bikes here, right? And then now they have money, so they have Super Bowl commercials of really good looking people riding the bike. So my mom knows what it is. She's like, isn't this your database, right? Uber came out with a Peloton, a scheduler for Kubernetes. There's a Peloton self-driving truck company in Silicon Valley. So for these reasons, as well as engineering reasons, which we can take offline, the Peloton project is dead. We killed everything and we're starting over. We don't have a new name for the system. Again, my wife getting pregnant sort of has stymied my plans, and I wanted to be here to announce, hey, here's our system. But again, we're not ready yet. The only thing that matters on this slide are the first two things here. I've already said this before, but we're designing the system, we're training and modeling our first-class engineering component in the system. That it's not something we're grafting on after the fact, we're building this internally and intrinsically in the system. And the last one that's super important if you're building a system yourself is that you want to have 0 restarts to apply any action. So in every commercial system and open source system we looked at, there's no system that exists today where you can apply an action and not have any possible action and not have to restart the system before that takes effect. So that's really important in our system today. So there was a post from Hacker News. I realize you guys can't read this in the back, but somebody posted the Peloton webpage to Hacker News and said, oh, look, here's the self-driving database system. But if you look at the GitHub page, it says clearly that we're dead. So someone looked in the commit history and actually found where the student originally named our system Poop Dish, but then I said that was a bad idea, so they had reverted to the name after my dog. Right, so now if you look on GitHub, the name of our system is Terrier, because that's named after my dog. So the reason why I'm freaking out about the system is because I can't name anything. So I couldn't name the dog, so we just named it after the breed. It's a Jack Russell Terrier, we just call it Terrier. It's taken me a year to design or come up with a name for the new database system, and then I got to name this kid in 3 months, which actually, I found out in the state of Pennsylvania, you can go for at least a year without naming your child. So my wife is not cool with that idea, but like, I have some time. So this is why I'm freaking out, because again, we now have to name a new database system as well as my kid, and I don't know what to do. So the last thing I'll say is that when we release the new system, one of the things that we're going to do to make research be easier for people is that we're going to package it up as a self-contained gym. So if you're familiar with like DeepMind and OpenAI, they have these gyms to do reinforcement learning, but basically like old Atari and Sega games that run in an emulator for you. And it makes it really easy to have a hooks and plug in to extract the data you need to train your models and apply actions and see whether you're actually doing the right thing. So this is really hard to do in database systems. Both in Peloton and other work that I've done, to prop up MySQL or Oracle, whatever you want, give it a database, give it a workload, and then train your models for these things. So what we hope to do is package it up as a gym that you can plop down on your laptop, plug in TensorFlow, PyTorch, whatever you want, and make it really easy and do rapid exploration of different models and approaches. So this is something we hope to release early next year. All right, so to finish up, I didn't talk about the modeling side of the policy, but I would say, as an aside, I think end-to-end reinforcement learning is not going to work for self-driving database systems. Right? It works for Go and other things where the problem domain is much more simpler in our world. And so this is not something that we plan on exploring. And some of the problems that I talked about today, like, oh, the dimensionality of the feature vector can change as the database system changes. That's why you can't use end-to-end reinforcement learning. The things we also talked about today were also about the engineering things you should do now, start thinking about how to have your system be autonomous in the future. So even if you're not even saying, like, this year we want to have our system be controlled by an autonomous agent, there's things you should be doing now, like modeling the state and the environment, and collecting that training data so that when you're ready to go autonomous, you have that infrastructure in place. Now, as far as helping my wife get through her pregnancy, like I said, I'm screwed on this, I don't know what to do. And trying to train for fatherhood in the future, my wife decided to put his dog in a papoose, and I walk around the house with this from now on. The dog doesn't seem okay with it, but this is how I'm learning. So with that, I'm happy to answer any questions. Thank you. And then there's a mic in the center. Alan, go for it.
Andy, a wonderful talk, as always. What puzzles me is why you are essentially trying to do stuff in a completely unaware way of the system design. You act as if you're trying to design, mechanisms for choosing parameters or whatever, which know nothing about the fact that this is actually an index and this is actually a buffer. I mean, we're not trying to design something which will be able to autonomously adapt any arbitrary piece of software. We know a lot about databases, how they're set up. We know a lot about increasing the buffer pools like that. So you could put quite a lot of model of the system in and reduce the complexity enormously. Why not?
Okay, so the previous question, I'll have the mic on. So Alan said, it seems like I'm sort of being blind to the fact that I'm trying to tune a database system and trying to build software that could tune any possible software system. And then if I apply domain knowledge about what I know about databases to the machine learning techniques we're trying to use, wouldn't that reduce the complexity and dimensionality of the problem and allow me to produce better results? I absolutely agree with you, yes. We don't know how to do that yet, just yet. So picking indexes, for example, we know that there are indexes we never want to use. We can look at the workload and say, nobody ever reads these keys, don't even bother. So yeah, we can use some initial pruning like that, but how you actually incorporate it in your policy when you make decisions, it's non-trivial, because again, what could be a bad index today if I do some early pruning might be a good index tomorrow, and now I don't have any of that training data on that. So I absolutely agree with you. We don't know how to do that just yet. In a sort of generalized machine learning approach, we are actually going to do, our first implementation will be basically not reinforcement learning, but a search tree where we do have database knowledge applied to it. Where I really want to go with this is like a 10-year pipe dream, is to have support what's called metacognition, meaning like I want to have the system learn what does it mean to be an index. So that sounds sort of like, sort of vague, but basically you're absolutely right. If I can learn why index helps me, then I can make better decisions of what indexes will help, will benefit my workload. That's where we want to go. In the short term, we basically want to do early pruning and then apply states. But everything I talked about today, like state modeling and I didn't talk, you're talking about the actual selection process, and that we're ignoring for now, at least in this talk. That's it? Oh, he's kicking me out. All right, awesome. Thanks, guys.
Alright, so did I explain session 1? Objective from Q unit. He is going to talk about estimating focus group by queries.
Thanks for the